In this lesson, we are going to be factoring perfect square trinomials and then doing a different type of factorization called the difference of two squares. So let's start with our perfect square trinomial factorization. What's special about a perfect square trinomial is that it starts off as a trinomial, which is a three-term polynomial, and once it's factored, it has two identical binomials, or binomial factors, which means they match each other. You can see the two examples here, a squared plus 2ab plus b squared. That's the general form for a perfect square trinomial, and we'll talk about the relationship between those three terms in a moment. But notice that you get a plus b and a plus b. They're the same. When you have two identical factors, you could call them the square of a plus b, for instance. In our second version of it, it's almost the same thing except for we have a minus 2ab in the center. Notice that the factors are also identical except for they're what we call differences, or they're both subtracting binomials. And notice that we have two identical, so we can say the square of a minus b. Now, there are a couple ways we could factor trinomials that are perfect square trinomials. One way is with factoring by grouping, which we learned a couple lessons ago. And another way is a factor pair shortcut, which I talked about when the trinomial starts with a 1. But a lot of times trinomials that are perfect square trinomials have numbers that are so large that factoring by grouping or factor pair shortcut doesn't seem like much of a shortcut. So I'm going to show you how the terms are related inside of a perfect square trinomial and how that can help you to know if the binomials will be identical and how to quickly factor if that is true. So in our example, we're going to factor the trinomials, use the above process if you have a perfect square trinomial. If not, use factoring by grouping. In other words, you can use what I'm going to show you as a shortcut if you have a perfect square trinomial. If you don't, then you resort to factoring by grouping from 2 lessons ago. So let's take a look at this first example, or this first trinomial. If you look at the original description for perfect square trinomial at the top, you see that we have a squared and b squared. I always start by looking for that in my trinomials. So in 81x squared plus 90x plus 25, I'm looking for squares in the first and third, and I notice that I do have those squares. So here's how I start it. I say, okay, I have squares. What do I square to get 81x squared? Well, that would be 9 and x, because 9x times 9x is 81x squared. What do I square to get 25? Well, the answer to that would be 5. Now, here's how you know you have a perfect square trinomial. If you take what's in the first square and the second square and multiply those together, 9x times 5, and then double that, go back up to the top, you can see where it says plus 2, that means double. If this is the same as the middle here, that means I have a perfect square trinomial. And I do, because 9x times 5 is 45x, and 2 times 45x is 90x. That means the middle of this matches the original middle of the middle term of the trinomial. This tells me that my binomials will be identical, and here's how we can factor. I'm going to set up 2 binomial parentheses, and I'm going to take 9x and put it in the first spot, and then 5 and put it in the second spot, and then whatever this symbol is here, which happens to be a plus, is what I'm going to use in each of those binomials. So 9x plus 5 times 9x plus 5, or the square of 9x plus 5, that would be the factorization here. Notice in this next one, I also start with the squares on the outside. So the square of 9x, the square of 5, so those are both squares. Remember the trick. You take what's inside, 9x and 5, and multiply them. And then you're going to see what happens when you double them. So 9x times 5 is 45x times 2 is 90x. That matches here too. So that tells me okay. And so you might be saying, what about that minus right there? How does that work? The way that works is that shows you how your binomials are going to eventually look at the end. So for 9x, I'm putting that in the first position, and then 5 in the second position again. But with the minus on 90x, it tells me to use subtractions instead of additions. So on the first one, it was plus 90x, so I had plus and plus, and then on the second one, it was minus 90x, so I had minus and minus. Remember, you could also say the square of 9x minus 5 is a compact way. So this is much faster than factoring by grouping, because with factoring by grouping, you would have to say 81 times 25, and you would have to get the factor pair that added to 90. Those are very big numbers, so it would take a long time to factor by grouping. Sometimes you have to factor by grouping if you don't have the perfect square trinomial, but in this case, we don't have to. So we're going to go ahead and use this shortcut, which we're glad to have. So let's take a look at this second row. So we have 49y squared we're working with and 4. So those are squares, right? We square 7y and we square 4, or pardon me, we square 2, not square 4. Now we're going to check. Remember, 7y times 2, 7y times 2, and then we're going to double it. 7y times 2 is 14y, times 2 is 28y. That tells us that that works. And then we're going to look here for the sign that we will eventually use for factoring. So remember, the binomials will each have a 7y, and they will each have a 2, and they're going to have a plus separating them. Remember, if you wish, you could call this the square of 7y plus 2. So let's look at the next one. I see I have a trinomial that appears to have squares on the outside terms. So I'm going to say, okay, this is the square of 6x. This is the square of 7y. And now I'm going to check the center. 6x times 7y. And then remember, you double it. So I'm looking here and here. So I notice 42xy times 2 is 84xy. So that works. And then remember, this symbol just tells me what the signs are going to look like. So when I go to factor, then my factors will be the same factors with the perfect square trinomial. 6x in the first position, 7y in the second, and then I'm using minuses because of that minus 84xy. The last one in this row, again, I'm looking to see for squares. I see squares on the outside, the square of 2x and the square of 3. In order to know if I have a perfect square trinomial, though, I have to take 2x and multiply with 3. That's this and this multiplying, and then double it. And I get 2x times 3, which is 6x times 2. That's 12x. You know, that doesn't work. 12x does not equal 37x. That's not the same. So up at the top here, it says, if not, factor by grouping. So I need to go to factoring by grouping to do this problem. So I would say 4 times 9 is 36. And then remember how that works. You're looking for the pair that adds to 37, which happens to be 1 and 36. So I'm going to factor by grouping. 4x squared plus 1x plus 36x plus 9. And now I'm going to group it just like we did in earlier examples. X times 4x plus 1. That's a 4 right there. It's a weird looking 4, but it's a 4. And then here I have 9 and 4x plus 1. Let me clean that 4 up a little bit. I don't like the way it looks. Okay, there we go. Now I have 4x plus 1 and x plus 9. So notice I did not use the the perfect square trinomial process for factoring that because it wasn't a perfect square trinomial. It has to be one of those to use that process. So I'm going to move into the other type of factorization, and this one's really quick. It's called a difference of two squares. Difference means subtraction. That's what subtraction, that's a fancy word for subtraction, difference. And two squares literally mean the square terms are squared. So here I have a square of A, a square of B, and a subtraction. That's how fast you know you have a difference of two squares. And a difference of two squares factors into two binomials that almost look the same, except one of them is a minus in the middle, one is a plus, or a difference in a sum. And you could change the order of these if you prefer. You could say A plus B, A minus B. That's okay. So For determining whether you have a difference of two squares, you can pretty much tell right when you look at it. Notice I have a difference right there. And this is the square of 9x, and this is the square of 5. That tells me that this will be a difference of two squares factorization. Two binomials, one of them is a difference, one of them is a sum. 9x in the first position and 5 in the second, and it's that fast. And if you wanted to say 9x plus 5, 9x minus 5, that would be okay too. Notice again we have a difference. So we're seeing, well, can we set up squares? Here's the square of y. The square of 12 is 144. The fact that I set that up tells me this factors. Two binomials, y and y, 12 and 12. And then I like to do minus plus, but you could do plus minus. The next one, a difference again. This is 7c to the power of 2 or squared and 1 squared. So the fact that I can set up two squares subtracting means that it's a difference of two squares. So I'll set up the binomials. We're going to do 7c in each one, 1 in each one, and then minus plus or plus minus. On the second row, I have a subtraction here. So I'm going to see if I can set up subtracting squares. If I can, 2x in here and 7y, which I could, it means that it'll factor into a difference in a sum, a binomial difference in a sum. So 2x minus 7y and 2x plus 7y. On this final example, even though 4x squared and 49y squared are squares, that is not a difference. That's a sum. So this is prime or non-factorable because you have to have a difference of squares for it to be factorable. So what you've looked at in this lesson would be the perfect square trinomial, which factors into two identical binomials, and I showed you a way to identify them so that you could quickly factor. If you have a trinomial that's not a perfect square, then that means you need to go back to factoring by grouping or factor pair shortcut if it started with a 1. And then finally, the difference of two squares is really quick to identify. It has to be subtraction of two squares, then it factors into a difference in a sum binomial. If you have an addition, it's non-factorable. It just means if you try to break it apart, you wouldn't be able to break it apart and find factors that work.